When it comes to our solar system, the relative motion between the planets and our star would be managed by space. No one would abandon their previous physical position, as it would be the space that would be stretching out around them. When you stretch a rubber band, an image used to illustrate the performance of space, the work is negative. Space would stretch in one direction, and force would point in the opposite direction. This negative work would be associated with the formation of space curvature. It would also promote the planet's late approach, moving it toward a future point, relative to the Sun. In the local case of our solar system, the stretching of space, being a negative work, would promote the late approach of the planet in relation to the Sun. In fact, when heading to perihelion, the closest approximation point to its orbit, a planet would only be returning to its resting position, which will never be reached. This approximation would exist only as a trend that would have been suspended to infinity, preserving the spiral movement of the planets through time. At this point, the viewer could ask, if the cause of the approximation between the Sun and the Earth were only the continuous contraction of time, or the consequent continuous expansion of space out of here, how, then, could the Earth go towards the aphelion, the distal point of its orbit? The answer exists only in theory, as you couldn't measure anything that might exist outside of spacetime. The solution to the problem would lie in the independent action of space on the masses of stars and galaxies, generating inertia. If this were accepted as a hypothesis, it would support the thinking of most physicists that intelligent life could not have arisen in the contraction phase of the universe due to the problem of entropy. Disorder should always be increasing, which would only be expected in the expansionary phase. So, let us continue to examine the isolated event of interaction between the Sun and its planets for a better understanding. If space acted on the mass of our star, changing its density in a transient way, even without direct registration, this would have reflections on time and on the relative motion of the planets. The curvature of space would be expected to vary over time, increasing or decreasing its extent. This would promote the relative and cyclical movement of the planets towards and away from the Sun. Even without abandoning its previous position in space, a planet would move closer to the star when its mass, even conserved, becomes denser and the total volume of the Sun decreased. As a result, the star should shine less brightly than usual. The increase in solar density would result in an increase in the tension between the star and the planet, predisposing the two to get closer. It is as if at first, the Sun pushed the Earth away from it when the curvature of space increased. This tension, related to the increase in potential energy, would decrease as the same density decreases, and the star increases its volume, resulting in a relative distance from the planet towards the aphelion, the point of maximum distance. In both situations, the planet and the Sun would keep their previous positions in space, since the curvature movement, whether for more or less, would have its direct register cancelled by the complementary contraction of time. This view of space-independent action shows that in our observable dimension, the only one that actually exists, time would accept two interpretations. One is the classic, which tells us that time would always be dilating after the Big Bang and towards our event horizon, accompanying the continuous contraction of space. The other alternative interpretation is that time would only be contracting less in the direction, not dilating. It is that the increase in the volume of the star would be associated with a lesser curvature of space, decreasing the potential energy and tension between the Sun and the planet, and resulting in the distance of the last one. Thus, the disorder could continue to increase and accompany the expansionary movement out of here. That would solve one of the spacetime paradoxes. To make this bold statement, you would have to see spacetime as if you were outside. It remains, for us, to solve the problem of the relationship between space and its messenger, cosmic radiation. One time contracted in the expansionary phase, until it reached levels that prevented its direct measurement, space would be at the mercy of its messenger to communicate to us any events in which it was involved. Include its own bending motion there. Light, which would encompass all other forms of radiation, would act as an unreliable messenger. This is because, to be perceived by us, it would have to assume a certain density, the form of clouded particles. This process of packing light gives it a dualistic behavior, known as quantization. It will result in the photon being scattered next to us, which will carry all information from distant stars and galaxies. You know that stars exist because of the photons they send us. Yeah, well, quantum mechanics has already demonstrated that quantization would not require measurable time. That is, the quantum is delivered to us, ready-made in our past. As we saw at the beginning of this video, without time there is no movement, whether absolute or relative. The universe would become virtually static, outside of time. If you pay attention to the concept of the Sun's future light cone, you would see that the depth of the aforementioned cone would depend on the existence of measurable time. Without time, the circular waves of light could not move away from the source. Similar to our past cone of light, physicists assume that the Sun's future light cone would have depth. The two aforementioned cones would be indirectly evaluated by the limited speed of light, since time in the past no longer exists, and the future has not yet happened. Note that the contraction of time in the inflationary phase would make its real arrow point to our future, not our past. As the future has not happened yet, what exists, for all intents and purposes, is the present moment of the universe. That's where we live our lives, floating in time. The most important consequence of the contraction of time within the future light cone at post-Big Bang events would be the virtual flattening of space. That is, even if space were to curve in the expansionary phase, influencing the density of stars more or less, and managing the relative motion between them, space would remain virtually flat, if it were indirectly described by light. The messenger would be lying and creating confusion in our way of evaluating space behavior. Perhaps, it would be better to think that the lie would not lie, it would just be waiting for us to find the appropriate interpretation for its harmonic behavior. When quantizing, light would polarize the extremes of energy in Maxwell's spectrum. That is, the ultraviolet and infrared would accompany the virtual flattening of space, approaching each other without ever touching. This flattening of space suddenly disappears with the inversion of the arrow of time as soon as the information is projected into the night sky. The time, held previously, can finally be measured by light, giving us the impression of the instantaneity of the event. The static universe suddenly goes into relative and continuous motion, unfolding into 3 dimensions in our past. Time, as you can see, would be a kind of dimension that would have been packaged at an earlier time, being responsible for our sense of depth. Time is managing the relative motion of galaxies in space.